So we are finally moving into the programming portion of this class. Okay, so we are just going to we're starting to ease into the whole thing. I think last time we were talking about the D flip-flops, and I believe for this class we did not quite finish the entire module. We were pretty close to finishing the entire module, and I think this was the last picture that I presented before the end of Tuesday. Okay. Maybe not this one, maybe the next one. I think we talked about the reset line. So I think it was this one that we talked about. So the reset line is what we call an active low signal, which means when it is low, we want to reset. When it's high, we do not want to reset in this particular diagram. And let me double check and make sure that I did turn on OBS. Yep, OBS is on. Okay, very good. All right. So when you look at this picture, and ignoring everything between the pins, okay, because that defines the interface to the device. So what do we have here is a resettable, gated, and clocked D flip-flop. Okay, so what does each word mean? Resettable means, at the beginning, when you power up a computer, all the bits are random, okay? They don't have any particular value. So what you want to do is to make sure that at least some of those bits are reset to a known state, and usually we want to reset it to 0. So that's what this reset line is for, is to reset a particular D flip-flop to 0, regardless of what it was before. And that's usually useful in two different occasions. One is during the power up of a device, and then the second one is when you intentionally want to reset the computer. Is that okay so far? So that's what the reset is for. Enable is basically saying who should be paying attention, okay? Because we will end up with a lot of devices, hooking up to the same data line. In other words, the data line is changing all the time. The clock is clicking all the time. So we have to say who should be paying attention this time. There's some data, okay? And the clock is going up and going down periodically, but we can control the EN to say who should be paying attention. Is that okay? So when you look at the input pins, reset is really just saying, okay, let's reset everything back to 0, and it's only used at the beginning of the operation of a computer. After that, we want to keep reset unasserted. In other words, we don't want to keep resetting devices. Data specifies what do we want to store. EN specifies who is supposed to store. And then clock is specifying when to store. So we control the time. We control who should pay attention, what data should be stored, and that's it. Okay, reset, once again, is just used at the very beginning of the operation. Q is the only output pin, and that's basically really just what have you remembered. Okay, so keep telling the world what you have remembered at that point. So are we okay so far with this picture? Okay, so with this picture, so if you abstract this picture, okay, so draw a big rectangle, okay, around all the pins. So draw a big old rectangle like that, and then you just shrink the big rectangle down to a single tiny little chip, okay? So imagine that is what you just did. Then we can scroll down and look at the last design here. Okay, let me back up one level so we can see the entire thing. One more. There we go. Okay, so when we look at this thing, remember what I said earlier? Shrink the big old thing back all the way down to a single rectangle. Now we have 8 instances of those little rectangles. So each one is a resettable, gated, edge-sensitive D flip-flop. Okay, so what is this thing doing? Well, when you look at this thing, it looks like a mess, but it is not really that big of a mess. There's a certain regularity to it. When you look at the clock line, okay, which is this line here, it is actually shared by every single D flip-flop as a component. Okay, so they all share the same clock. When you look at EN, it is also shared. So when you look at EN, it goes to every single bit D flip-flop. When you look at the reset line, it's the same thing. So the reset line is here, and you can see how it is quote unquote multi-dropped into each and every single box. The only one line that is not shared are the data lines. So when you look at this entire thing as one single device, it has one data pin that has 8 individual bits. Okay, that's why you see an X8 here. It means that input pin has 8 bits. So what do we do with that 8 bits? We use a splitter. We split those 8 bits into individual bits so that the first D flip-flop is only responsible for bit 0. The next D flip-flop is responsible for bit 1, and then the last D flip-flop is responsible for, guess what? Bit 7. Is that okay? So this entire device is almost just like a multi-bit version of a D flip-flop. What about the output? What do we do to the output of each individual single-bit D flip-flop? Take a look. Tell me what we are doing with it. How does the individual output of each D flip-flop relate to the output of this entire device? What do we use to connect those? What does it look like to you? Go ahead. It's a merger, which is also known as a splitter, except you flip the direction, right? So it is really just a merger. In other words, we take the output of each individual D flip-flop, then we merge all those output back into a multi-bit output pin. And that's it. So when you look at this entire thing, oh, by the way, how do we call 8 bits together? A byte. Very good. Okay. So when you look at this entire thing, one way to call it is a byte-wide, resettable, gated, and edge-sensitive D flip-flop. It is just like a regular D flip-flop, except it is multiple bit wide. But that's a pretty long phrase to say every single time. So from here on, we just say it is a register. It's a register. So a register is nothing more than a resettable, gated, edge-sensitive, multi-bit D flip-flop. Is that okay? So if I call this a register, which is a much simpler word than the whole phrase of resettable, gated, edge-sensitive, multi-bit D flip-flop, what is that telling you? Do you think we're going to use the word register a lot from here on? Because otherwise, I wouldn't give it a simpler name, right? Okay, so this is what a register is. So the first thing that we want to kind of think about is, what do we use a register for? What do you think this can be useful for? You can store a char, you can store an unsigned 8-bit integer, you can store a signed 8-bit integer. If you string 8 of these things along, you can even store a double. A double is only 64-bit wide, right? 64 divided by 8 is 8. So 8 of these things, is wide enough to store one double. Okay? So this is the simplest memory device inside a processor. It is called a register. But then what about the SR latch and all of those things? Well, those are all inside each one of these devices now. Okay, so collectively, the most useful, lowest level device to store information inside the processor is this thing here. In other words, this entire module is starting off with the simplest device, which is an SR latch made out of two input NAND gates, and is building all the way up to this final product here, which is the most elemental memory device inside a processor. That's the whole purpose of this module. So are we good so far? Okay. All right. So now that we know what a register is, and this really is the end of this module, what are we going to talk about next? Because we are going to talk about okay, let me go back to this class here. So what we're going to talk about now is So how do we build a processor? We have talked about a lot of the really useful ingredients to make a processor. So let's go back in time, okay, and revisit the pine forest that we have traversed so far. We talked about NAND gates. At the very beginning of this class, we talked about NAND gates and 2 P transistors and 2 N transistors, right? And then we say that, oh, with that, we can make up all the gates that we normally need, which are the NOT gate, AND gate, OR gate. Okay, that was at the very beginning of this class. And then we moved on to talk about adders and subtractors, right? The carry look ahead adder and the borrow look ahead subtractor. We talked about how we represent values, signed versus unsigned, okay? We also talked about how to store values that are not integers, and that's why we have to talk about doubles, okay? And then we talk about memory devices. So right now at this point, we have some of the most important ingredients of a processor already discussed. We have a few more before we can actually get to talking about the processor. So we have 3 more topics to go over, but I do not have slides for these things. I do not have my own modules to talk about these things, because guess what? Logisim has a pretty good explanation of these devices already. So we're going to talk about ROM, we're going to talk about RAM, and we're going to talk about multiplexers and demultiplexers. Okay, so all of those are in Logisim. So when you're studying this portion of your notes, okay, for the next exam, I do not have any module that I have written for this, and you have to refer to the help of Logisim. Is that okay? So I'm going to help you guys to find where there is, and then we'll go talk about it. So I do have Logisim already started up. I'm going to close all of that just so that I can show you how to find it on your own. Okay, so that's the preview exam. We can close that too. And let me go back here. Okay, so I'm going to start up Logisim again. And without, well, it loaded my own processor, but I didn't really have to do that. You go to help, and then you go to library reference. And the first thing we want to talk about is ROM. So where do you think ROM is going to be? Looking at all of these subcategories, where do you think ROM is? Memory devices, because ROM stands for read-only memory. Okay, and that's why it's a memory device. You click on ROM, and here is the full description of what a ROM is. It describes the behavior. It describes what the pins do. Okay, so this is all good, but remember, the next exam is also going to be open book and open notes. But this is just a help from a particular program. So how do if I want to print this out so that I have this as a backup in the next exam, how do I go about doing that? You can copy and paste, you can take screenshots, but those are very ineffective ways of getting content onto paper. So how would you do this? Okay, so what is the first question that pops up in your mind when you read something like this that seems to have pictures, hyperlinks, and seems to have like different types of, it's in HTML, okay? But where is the HTML? But the entire program is inside a jar file, JAR, jar file, right? So you go like, okay, so inside that jar file, there has to be components, okay? And one of the components, or some of the components, is the documentation of the program itself, okay? So you go like, okay, so how do I know, what is the process to break up the jar file back into the individual components? So how would you go about doing that?
Open it up with like 7-zip.
You can open it up with 7-zip, or the easiest way is to ask Google, right? How do I decompress a jar file? Or how do I look into the content of a jar file? Okay, so if you do something like that, you will notice that a jar file is nothing more than a zip file. It has exactly the same format as a zip file, except it has a different extension. So the Windows knows what to do with a zip file, which is just, okay, I can decompress it, I can show you what is in it. But when there's a jar file, Windows knows, oh, I can run this using Java. That's the only reason why they have a different extension. If you rename a jar file from JAR as an extension to ZIP as an extension, Windows would now say, oh, it's just a compressed folder. I know how to decompress it. Is that okay? So let me show you what you get when you decompress a jar file. And the jar file, JAR, actually stands for Java Archive. That's what the AR is for, is from archive. Okay? So the path to mine is in the root folder. So let me go to another terminal here. And I'm going to remove the one that I already have here because I have done this before. Oh, okay, maybe not. Okay, so let me remove that folder and make that folder again. And then I go to that folder. And then I just say, oh, unzip the file in the previous folder called logisim generic.jar. And I do it on the command line. You guys use Windows or Mac OS X, you do not have to do it on the command line. Okay? You just rename the jar file, right click on it, rename the extension to ZIP, then Windows knows what to do with it. Okay? You might want to make a copy so that you keep the jar, but you also have another copy with a zip extension. So that way you're not going to lose the jar file when you do something like that. So this is after it's fully decompressed. The first thing you notice is, oh, the source code is fully available. This is actually open sourced. So if you ever have the itch to go like, well, I want to play with this program, I want to see how it works, it's completely open-ended. Okay, the source code of our Logisim is right here. You're looking at it. But we are not interested in all this stuff here. Instead, we're interested in the documentation. So you do an ls, or in Windows, you just kind of navigate the folders a little bit. And we'll say, where do you think that documentation is located? Under doc. Yep. Okay, so you go, all right, we go into the doc folder. And what does that look like to you? Which one should I look into? What is that, EN, DE, ES, and EL thing doing? And then PT and then RU. Those are the languages, okay? RU is Russian, ES is Spanish, EN is English, DE is German, and so on, okay? So I can only understand English out of this collection here, so I'm going to go to EN, right? Now, if you say, okay, I feel more comfortable with some other language, okay, fine, go to the other language. It's not a problem. So I go to EN, and then I see a bunch of subfolders here, contents.xml. That's really just a XML file to describe the content in this particular folder. Then we got HTML, icons, img-guide, img-libs. So which one should I explore next? HTML seems to make sense, right? Okay. So we go to HTML. Oops, HTML. There we go. And we see contents.html, guide, index.html, libs, and so on. So if you have taken a web class, you know that index.html is usually the starting point of documentations, okay, of web documentation. So we'll start with that. Oh, by the way, how do I open an HTML file? Now, I'm using the command line, so it's a little bit more archaic, okay? But if you're using Windows, you don't even see the extension HTML. What do you see instead? The browser symbol, right? The browser icon. You double click on that thing, and it will open up using your favorite browser, okay? So in this case, I'm just going to say, okay, Chrome, open index.html. Okay, Chrome is not found. Why is it not found? I'm pretty sure Chrome is installed. Maybe it's Google Chrome. Yep, Google Chrome index.html. And here we have access to the documentation. Welcome to Logisim. Where are we supposed to go again? Library reference. Okay. So you go to library reference, and we want to look into memory devices, right? So we go to memory devices, we click on ROM, And guess what? We are now looking at the documentation as an HTML file inside a browser. Why did I go through all this trouble? What was I trying to do in the first place? Yeah, exactly. We're trying to print it, right? So at this point, what do? Please tell me you know what to do. Control P, right? Shortcut, and then just change the settings to your liking, double-sided, single-sided, whatever. Okay, and then just click print, and you're all done. So this is how you can print out the reference pages from Logisim onto paper and bring that with you in the next exam. Okay? Now, don't do it just for the exam because if you're going to do it, you might as well do it earlier so that you can use it as a study guide as you work on the homework assignments. So I think this can be very helpful when you are working on this portion of the class. So are we okay so far? Do you guys understand the process to print out the content as help material in Logisim? Okay? All right.
One thing I think that you should be mentioning is that sometimes in Windows, file extensions are hidden.
Yeah.
So if you go up to the ribbon and you click on View, it'll let you show file extensions. So then you can change the jar to a zip.
Yeah. It's really annoying. I do not like that part of Windows at all. Yes, by default, it hides the extension. You have to re-enable extension to see the extensions. All right, so let's go check out what a ROM is then. Okay, so I'm using the Logisim documentation now to explain what a ROM is, and it makes sense to me because we're going to use Logisim to implement our processor. In other words, the components we're going to use is consistent with this documentation. So it does not make sense to me for me to write separate documents when it's already here that is consistent with the tool that I'm planning to use. All right. So right now, right here it says ROM, which is read-only memory, consists of 60, can store up to basically 16 mega. Yep, 16 megabytes. Or 16 mega values. Okay, it says it's just a value because each value can vary in terms of bits. So the next clause of the same sentence says each value can be up to 32-bit wide. It can be 1 bit wide, can also be up to 32-bit wide. But you can have 16 million of those, up to 16 million of those. A circuit can access the current values in ROM, but it cannot change them, and hence the name read-only memory. The user can modify individual values interactively using the poke tool, the finger tool, or the user can modify the entire content using the menu tool. I will show you all of those things. And it has got 3 ports. It has got the A port, which is address, the cell port, which means select, and then the D port, which is the data port. So instead of me just reading all of this stuff to you, okay, we'll just go ahead and use one. Okay, we'll just go put one into a design and see how it works. So I'm going to close this first. Okay, I'll make a new one and then close the other one because this is a little bit too distracting, too much stuff on it. So I would use. Uh-oh, it just closed it. Okay, that's fine. We'll re-enable. Do it again. Nope. 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 I repeated the wrong command. Did I do it in the other tab? Yep, the other tab. There you go. All right, well, add new circuit. Okay, just call this test. There we go. Okay, so now we can slap on a memory module. In memory, we can slap on a ROM. And we can zoom in just a little bit so that we can see better what a ROM looks like. All right, so this is what a ROM looks like. And the characteristic or the properties of the ROM, there are only a few, okay? One is the address bit. In other words, how many bits are we going to assign to the port A? Right now, it is 8. Now, how many bits you assign to the address port determines how many locations is going to be in the ROM. So what do you think is the number of locations in this particular case when the address has 8 bits? How many individual locations can I address when you have an 8-bit address? The address itself is 8-bit, which means it can go from 00000000 all the way to 11111111. So how many unique locations can I specify when the address is 8-bit wide? Yep. 256. Okay. Okay. So do you guys see why there are 256 locations that I can address when the address itself is 8-bit wide? The location of the first location has an address of 00000000. What do you think is the address of the next location? 00000001. Okay. What about the next one? 00000010. What about the next one? 00000011. Does it make sense? So you keep incrementing that value until it becomes 11111111. So the question now is, how many distinct addresses can I specify using an 8-bit number? That's basically what the question is.
2 to the 8th, but where are all the bits? Is it not showing on the ROM chip?
Okay, so when
It
you,
seems like a lot more than I see if those are bits.
those are just a portion of it. Okay, so if you want to see the entire content of the ROM, you can use the right click and then you go to edit content, then it shows the entire content. So in this case, there are 256 values on the screen already, and you can see each row is starting with the address of the first byte of that row, but in hexadecimal. So the first row starts with 00, which basically means we are looking into the content of the ROM, and this is the content at location 00 in hexadecimal. This is the content at location 01 in hexadecimal. This is the content at location 08. This is the content at location, now this is going to be the upper of the hexadecimal digits. This is going to be, which one? 0C. Very good, because it's 12 in decimal. It is C in hexadecimal. So that's 0C in hexadecimal. D, E, F. And then the next row starts with 10. And then we have 11, 12, and so on. So if I just randomly pick a location like this one here, what do you think is the address of this? It's going to be E, because we know this entire row starts with E. And then the next digit is going to be 0, 1, 2, 3, 4. Or you can count backwards. F, E, this is D. So this is location ED in the ROM. But ED is in hexadecimal. E is 1110 in binary. D is 1101 in binary. So if you want to refer to the binary address of this location, it would be 1110 1101. Is that okay? Do we understand how to specify a particular location in ROM? Then what about all the zeros that we are seeing here? If the addresses are going to be like, from 00 to FF, how come we're only seeing zeros in here? Those are the content. That's the content of each location. So you have to remember to differentiate between the address of a location versus the content of a location. Question?
No, I said it reminds me of a lot of pointers.
Exactly. This is exactly what pointers are about. Because what does a pointer store? The pointer stores an address. How do you get to the content at that address? Dereference. Exactly. All of that stuff is now coming back. So this is the reason why I really need C and C or C++ as a prerequisite of this class. Java doesn't get the job done. because Java has no pointers. So people who have only studied Java do not understand what a pointer is, what an address is, or what dereferencing is. Okay? I hope no one here only has taken the Java class. I mean, you can have taken C++ and a Java class, that's fine, okay? But with only a Java background, that person would not be able to understand these concepts. So are we good so far? So now we can put in some random contents if I want to, okay? So let's go ahead and put some content into this ROM. So if you want to do it interactively, you can just go to location and just start to specify the content, like 7D over here, 0E over here, and over here, let's say this is 3.1, and then over here we'll give it a F2. Okay, so I have just planted some random values into the ROM, and once you have done that, if you say that, oh, this is kind of important to me, I might want to save it, you can just click save and save it to a text file. The format of this text file is really simple, so you can open it and take a look at it if you want to. But for the most part, we don't really need to know what the format is. And there's no default extension either. But because there's no default extension, I would just add .rom as an extension, just so that you remember this is the content of ROM in Logisim, so that you don't mistake it for something else. Okay? So, but I'm not going to save it because the content of this ROM is not particularly important. This is just an example. So I can now close this window. Okay. Then the next thing we want to do is go like, okay, but how do we use this ROM? Now that we know that it consists of 256 locations, starting at address 00000000 all the way up to 1111, and we have planted certain values into certain locations. How do we make use of it? In other words, how do I say, hey, ROM, pay attention. I want you to recall the content at location blah blah. Okay, how do we do that? Well, let's hook up some input pins and output pins to this thing so that we can actually interact with a component like this. This is something that I encourage you to do with just basically all of the components that we'll be using for the processor, so that you can understand how a particular component work. Okay, so what I'm doing here is I'm using some input pins to match the ports. So this is going to be matching the address port. This is matching the select port. And this is going to match the output port, which has 8 bit. So we have to change the width of the output pin to 8 bits so that we can actually see all that stuff. Okay, so the first thing we notice, the simulator is actually running at this point. The first thing we notice is, hey, how come the output, they're all X's here? Well, that has to do with the select pin here being a low. In other words, this ROM is currently not selected. If a ROM is not selected, it doesn't do anything with the D port. It doesn't specify any content on the D port so that somebody else who is also connected to this wire can specify content. Is that okay? So the first thing you need to do if you want to make use of a ROM is to say, okay, you're selected now. Okay, pay attention. So now you use a poke tool and you say, okay, ROM, pay attention. So as soon as you ask the ROM pay attention, it does that. And what it does is it will read in whatever the A port has and then say, that's the location that you're interested in. And it will highlight that location for you and say, oh, you are trying to specify location 00 in hexadecimal in this case. Well, that's because our input pin really is 00. Is that okay? So that doesn't seem very interesting. So let's go into the ROM and find out where we have some actual content in the ROM. So we can go back to edit content. And let's see which one we should find. How about this one? Okay, we want the output of the ROM to be 7D. So what should I specify as the input to the A port? What is the address of that byte? What is the address of the byte with the content of 7D? Looks like it's going to be 5, 4. Okay, it's 54 because we count from 0. So it's 54. Okay, so we switch back. You can leave that window up if you want to. And then we switch back to Logisim and say, we want 54. Unfortunately, this is all in binary, not in hexadecimal. So now you have to, in your mind, translate 54 in hexadecimal back into binary. 5 is 0101, 4 is 0100. Okay, so we'll go ahead and specify that. 0101, 0100. And it is addressing 54, but the content is not what we want. And I think I know why. I think it's because we have been simulating since the beginning. So we have to reset simulation and then enable simulation again. And then do one more time. 0101, 0100, and enable it. There we go. So there's our 7D. So once you enable the ROM, you specify which location to read, then the D port will just output the content at the addressed location. Then you go like, is that really 7D? 0111, 1101? What do you think? How do we translate a binary bit pattern back into the hexadecimal digits? Break it up in groups of 4, right? So we break it up into, so usually you want to break it up in groups of 4 from the right, not from the left, okay? Unless you know the whole thing has a multiple of 4 bits, okay? But in this case, we can do it from the right. 1101, you look up the table. What is 1101? In decimal, it is 13, because it's 1 plus 4 plus 1. Excuse me, it's 8 plus 4 plus 1, which is 13. But when you look up the hexadecimal digits, 13 is matching D. Very good. Then the other 4 bits, which is 0, 1, 1, 1, that's an easier one, because 1 plus 2 plus 4 is 7. 7 is just 7 in hexadecimal. So we do get 7D back. Is that okay? Cool? Now, just to make it easier to remember what we are doing, we can look at ROM as a read-only array. Okay, you can just look at it as an array. So what I'm doing right now is I'm just going to my tablet. I will project the tablet in just a little bit. I just need to navigate to the book first. Okay, so okay. So what you can do mentally to equate this to concepts that you have already known is basically to say that the D port is the output, okay? It is using the ROM as an array, and we're using whatever content at the A port as the index. In other words, you look at ROM as an array, and then you look at whatever content at the A port as the index to the array. Whatever that particular element in the array is, the content is presented at the D port. So I'm not sure whether this helps or not, because I think for some people it might actually be more confusing, but I think this is actually one way to look at a ROM and be able to associate it with things that you already understood. Is that okay? Are there any questions about this kind of C++ way of looking at a ROM? Okay, all right. Okay, so ROM is done. ROM is fairly simple because you can only read from a ROM. You cannot overwrite content in a ROM. So we say, okay, if that is done, let's move on to the next one. So we go to project, we add another circuit, and this one is test RAM. So this time we're going to look at a RAM component, which is here. And just like before, we just slap the RAM component on and go like, whoa, this one has got a lot more ports, okay? There are a lot more things going on with a RAM module. But you might notice that the properties are about the same. They're not completely identical, but they're pretty close. You still have the address bit specification, which also determines the number of locations in this RAM. So once again, if you specify whatever number as the address bit, let's call it n, then you will have 2 to the power of n locations in the RAM. So since I specify 8 here, we have 256 locations. If I specify 10, I would have 1,024 locations. If I specify, let's say, 13, I would have basically 8 kilo, okay, about 8,000 locations. Is that okay? Each location also has, the next number determines what is the width of each location. So right now, each location is only 1 byte wide. I can increase it to 16-bit if I want to, so each location is now 16-bit wide. Is that okay? But it also has one extra thing, which is data interface. We'll keep this one, using the default and not change that. So we'll keep the default. So now we go back to the picture and go like, okay, what are these things doing? Well, A is really just doing the same thing as before. It allows you to specify the content of which location are we interested in, just like ROM. D is about the same as last time. In other words, if you say, I want to read back the content of a certain location, then D is going to do exactly the same thing as in ROM. But it also serves a different purpose in the RAM, and we'll talk about that next. Sel, S-E-L, which is select, is doing the same thing just like a ROM, which is basically saying, of all the chips, is this one selected? In other words, should this particular RAM chip be paying attention and doing anything? Because if selection is a 0, it will just ignore everything, and it will not drive the data port. Okay? So with A, Sel, and D, it's almost exactly the same as ROM. But what about the other things? Well, here is one thing that we have seen before. It's a clock. Okay? So as it turns out, RAM only updates the content on the rising edge when it is selected. Okay? So from that perspective, it is almost like a register. It only updates on the rising edge. Is that okay? What about the other two? Well, let's look at the last one first, and then we go back to the middle one. The last one is clear. It says here when 1, reset content to 0. So it's kind of like the reset pin of a register, and it serves basically the same purpose. When this pin is a 1, when CLR clear is a 1, then the entire content of this RAM is going to be reset to 0. Okay? It's really useful when you're powering up a computer so that you can count on the content of RAM being all zeros. So this is the mysterious one. This is a mysterious one because it's called a load pin. It specifies, it's a really bad name for that pin. It really should have been called read-write, okay? So if LD is a 1, we are reading from the RAM. If LD is a 0, we are writing to the RAM. If your intention is to recall the content of a location, you want LD to be a 1. If your intention is to overwrite the location of the RAM, then you want LD to be a 0. So that allows you to specify, oh, I want to overwrite the content of a particular location. That's one thing a ROM cannot do, because ROM is read-only. But RAM is read-writable. Okay, wait, that doesn't make sense, right? ROM is read-only. That explains why it's called ROM ROM. What about RAM? What does RA stand for? Because that doesn't seem to be read-writable. It's random access, exactly. So RAM comes from random access memory. All right, cool. So what do we do next? Yep.
What
Yeah.
does it mean for something to be random access?
My understanding is random access only refers to which location you want to access. So you can access, so the pattern of accessing doesn't have to be sequential. So from that perspective, ROM is quote-unquote random access as well. But that's just my understanding of what they mean by random access. Yep. No, no, I don't think random access refers to that. Um, we can look it up. Shouldn't take much time to look it up. So we look up random access memory. So it does specify that it allows data items to be read or written in almost the same amount of time irrespective of the physical location of data inside the memory. In contrast, other direct access storage is sequential, and that's why it's not random access. So nothing in the word in the acronym RAM actually suggests that it is overwritable. But our understanding of RAM is it is overwritable, which is not really a part of its name. Is that okay?
So essentially, it's doing all of its writing at the same place that it does its like memory storage stuff also. Whereas opposed to, I mean, it does it all at the same spot, right? That's why it's not overriding it.
It has to do with the circuitry inside the RAM that allows you to. So if you want to access location 0 versus location 255 in the case of our example, it will take the same amount of time. As opposed to when you're looking at CD-ROMs, okay, you're accessing different locations would require different amount of time because you have um, because it's all sequential. Yep. It's constant time, but random access, the word random access, basically says, you can go to different places and it doesn't incur additional cost. So yes, yes, it is like an array as opposed to a linked list. Because with a linked list, it is not constant time. Things that are at the end of the list will take a longer time to access. Things that are at the beginning of the linked list will require a shorter amount of time. But none of that relates to the most important part of what a RAM is that the content can be overwritten at runtime. So that part is just not, for some reason, not encoded into the name, of what the device is. But we all understand that that is the case. All right. So yeah. So I'm gonna just stop there. All right, so now we want to look at this ROM and go like, okay, how do we understand the operation of RAM? So what we do is just like before, except this time we have a lot more input pins because there are a lot more ports that we have to specify. Okay. And let's make a input pin here as well. Okay. So this is going to be an 8-bit input pin. This is going to be another 8-bit input pin because they are all one connects to the address port, and the address port we have already specified to have 8-bit wide. And then the other one connects to the data port, which we also have specified to be 8-bit wide. And then these will just, one goes to the select, one goes to the clock, one goes to load, which is controlling, read write, specification, and the last one goes to clear. There we go. All right. So the first thing we want to do is let's put some content into this RAM. Yep. Huh?
The facing. We should change the facing.
Oh, right. The facing. Thank you. Because the dot is on this side. Okay, facing west. Good catch. There we go. Okay. So the first thing we want to do is let's put some content into this RAM. Okay. So the first thing is you have to specify which location do we want to change. So let's pick a location that is already on screen. Let's pick this location. What is that location? What is the address of that location? 0C refers to the first thing of a row. So if this is C, D, this is E. 0E is the address of the location that I want to change, which is this guy here. But I have to specify 0E in binary. Okay, 0E itself is in hexadecimal, but the input pin is not in hexadecimal, it is only in binary. So I have to convert 0E into a binary number. What do you think that's going to look like? 0 is easy, right? 0 in hexadecimal is what in binary? It's 4 zeros. So you have to be specific. So 1 0 in hexadecimal is 0 0 0 0 in binary. You always want to make sure that it's in a chunk of 4 bits. Okay? What about E? E is going to be 1 1 1 0. Now, there's a quick way to do that because F is 1 1 1 1. E being 1 before that is 1 1 1 1 minus 1. And that's why we got 1 1 1 0. Now, the more you use this conversion, the more likely you're going to have to, you will actually memorize all of these things, not even intentionally. So we'll specify that location, which is 1 1 1 1 1 0. Okay, so we got that. You guys can tell me how you want, what is the new content at that location? How do you want to change, what do you want to change it to? It's up to you. Any suggestions? Hmm? All ones, okay. Huh? 2 Fs, okay. They are actually the same thing.
No, I mean 2.
Oh, 2F, okay. 2 and then an F, okay. Because I didn't understand whether it's 2 followed by an F or twice F, right? Okay. So, okay, let's say 2F. So 2F is 0 0 1 0, that's the 2, and then 1 1 1 1 is the F. So it's 0 0 1 0, and then 1 1 1 1 as the F. Something is not working here. I don't see any changes. Well, first of all, it's not even turned on. Okay, the chip has not been asked to pay attention. So it has been daydreaming all this time. Okay, let's say, okay, RAM chip, pay attention. Oh, okay. So you want to do something about this location. Okay, fine. Okay. So now we have to look at all of the other pins and go like, well, we don't want to do clear because that's just going to make everything 0 again. It's already 0. So forget about the clear pin. What about the LD pin? The LD pin specifies whether we are reading from the RAM or writing to the RAM. Are we changing or are we just reading back? In this case, we are changing, and 0 is the right value. Okay, then how come it's not changing? Because the clock, okay, it only updates the content on the rising edge. And right now the clock is just sitting at a 0. It is not a rising edge, right? So what I need as the last component or the last step of the process is to turn the clock from a 0 to a 1. Okay, so let's do that. From a 0 to a 1. Ding! We got it. Cool. Okay, so let's write to another location. Okay, let's write to, I don't know, how about this location here? Okay, I'm going to point to it over here. So I want to write to this location next. So what should I do? Well, okay, first thing is let's put the clock back to 0, okay? And then what do? We specify the new location. The new location is 03 in hexadecimal, which is 0 0 0 0, and then we have 0 0 1 1 with that location. And what do you want to be its content? Okay, let's go with your suggestion, all ones. Now, when you say all ones, you have to specify the base. Do you mean 1 1 in hexadecimal, or do you mean 1 1 1 1 1 1 1 1 in binary? FF. Okay, in hexadecimal. Okay, so FF in hexadecimal means the data needs to be all ones. Okay, so we have everything set up at this point. It is paying attention. We are specifying a write operation. We just need a rising edge on the clock. Click, done. All right, very cool. It doesn't do anything because it's edge sensitive. So if your clock is a 1 already, you can change the data, you can change the address. It doesn't do a single thing. It's just like a register, just like a edge sensitive D flip flop. It's only at that instant when you have the clock to switch from a 0 to a 1. Only at that instant it will pay attention to the data line and update this content. Okay, so this is all cool. Okay, so now I can play with the address line to go to location 0 and not to do a single thing. So the next thing I want to do is to say, I want to read back the location, or I want to read the content at location 0E, which is the 2F. So what do? Well, it doesn't seem very difficult, right? I mean, I have to specify 0D. Okay. Oops, oh, that's E. I have to specify 0E to get to the right location. But remember, this time it is a read operation. So with the read operation, the clock is useless for read operation. But I do need the LD pin to be a 1 to specify a read operation, right? Because the LD pin is specifying the direction. Are we changing the RAM or are we reading the RAM? So it's responsible for changing the direction. So let's do that. So that we are expecting 20 to be over here because that's what we should be reading back. We click it and go like, whoa, something bad has happened. How do I know something bad has happened? Because it's red. Now, why do you think red is usually saying that something bad has happened? It is somewhat of a tradition, but I think it's built into our genetics. Yes.
It's because red's like a really bright color.
And why do you think it's a bright color?
Red and bright color because poison apples like really red.
But why? Why do you think we automatically, without even having to be taught, understand red is whoa? Yep. Because it's the color of blood. Yep. No, I'm not. I'm serious. Okay, I think it's genetically coded. In other words, we might have ancestral branches who did not have that hard coded into the brain, so they get a cut. They got a limb chopped off and go like, oh, red stuff is coming out of myself. I guess it's okay. Keep limping along. I'm just gonna go home, right? As opposed to somebody who has that genetically coded and go like, holy smokes, this is bad. I need to do something about it, right? Or other people will see and go like, okay, this is bad. We need to do something about it. So I think that's genetically coded. But that's my theory. If you don't believe in evolution, just ignore all of that. Yep. Huh? Pain would be one part of it too, but when you're looking at somebody else, somebody else is bleeding, you understand that is a bad situation, as opposed to someone just kind of drooling, right?
So like, do we use green because like vegetables and stuff? When you see green, you think something positive. That could possibly be.
Actually, there's another reason why we recognize red. It has to do with ripened fruit is usually red, and that gave early primates a clear advantage over others who do not have color vision, because you don't have to climb all the way up to the top of the tree only to find out that fruit was not ripe. You can just go like, nah, not today, maybe tomorrow. Okay, so getting back to the topic here. So when you see something that's red, something that has gone wrong, you click it, okay? And it shows you something really kind of interesting. It's like EE1E1111. What does that mean? Well, it's telling you that we have problems, but only with certain bits. So the bits that are actual just ones or zeros sometimes, they're fine. They don't have a problem. We only have a problem where the E's are. So why do you think we have problems with the first, the most significant, the second most significant, and the fourth most significant bits? Why do you think we have a problem? Well, to understand that part, you have to understand what is 2 and how it is different from 1111, 1111. So what I'm going to do here is I'm just writing down this stuff onto my tablet, and then we'll switch over to the tablet for the time being. Okay, so 2F is the output of RAM. In other words, the RAM component is trying to scream to you and say the content of the location that you're interested in is 2F, okay? But 2F is in hexadecimal, so what does it look like in binary? It's 0010, which is the 2, 1111, which is the F. So your RAM component is really trying to scream at the data port and say, oh, it's it's 00101111. It's trying to scream that as loud as it possibly can. But your input pin is saying, no, I want that wire to be reporting 1111, 1111. Okay? So the ones are not a problem. Okay? So when you match up 1111, 1111, this is from the input pin. That's not a problem. Okay? They agree. No problem, agreed. No problem, agreed. No problem, agreed. Uh-oh. We have a situation here. If they're connected to the same wire, okay, which means electrically they are connected. The RAM is specifying, I want this wire to have a low voltage. The input pin, which is under your direct control, says, no, no, I want it to have a high voltage. So what do? E, error, okay? That's why we got an error bit there. The next one is fine because they agree that it should be a 1. And then we have another error and another error here. And that is the reason why we got EE1E 1111, because there are certain bit positions that are disagreed upon. Is that okay? So what do we do? Because that's an input pin, it's not really designed to report back what is the content of something. Okay, so let's go back to LogicSim and fix that. Because it seems like what we really need is a output pin. So we will need an 8-bit output pin. Take away this connection. We don't need that anymore. So go away. And instead, we hook up the output pin, and everything is good now. Yay! Except until next time you want to perform a write operation, then you cannot use an output pin to specify the new content that you want to program into the RAM. So now you have to disconnect this wire, reconnect to this wire, to reconnect the wire to the input pin, and then the next time you want to read, you have to disconnect the wire again, reconnect it to the output pin. That doesn't seem right to me. Yep. Aha! So we need some kind of a conditional thing, right? When you're doing this, use this. When you're doing that, use that. Right? That seems like something we need something like that. Okay. So we'll leave both pins here. But I'm going to remove the wires. Okay, so we'll take this wire it can always be there, okay, because even in a write operation, it's not going to interfere. It is this connection that cannot be there all the time. Okay, so the problem that we have at this point is the input pin conflicts with. Okay, so the core of the problem is the D port of RAM is not in only one single direction. Sometimes it's an output from the perspective of RAM. Other times it is an input into the RAM. So it can switch direction. It's a bi-directional port. And the direction is controlled by the LD pin, which specifies, are we reading or are we writing? That is the core of the problem. Is until now, every single pin that we see, which are the output pins of a gate or the input pins of a gate, they're always either an input or they're always going to be an output. Except now we have one port that is sometimes an output port and sometimes is an input port. Okay? So how do we work with something like that? Well, fortunately, in the library, we have under gates, we got something that is kind of interesting. It's called a buffer. And we want a buffer that is actually, we want a controlled buffer. Okay, so here's a control buffer. And, well, this is the first time we talk about, a control buffer. So if I'm being totally irresponsible and I don't explain it to you what a control buffer is, what are you going to do? You can complain to the dean, okay? But that doesn't help you immediately. Yep. Go to the help section. Exactly. Self-help. So we will go to the browser version of that, okay? So now we go back and then we go to, this is under gates. So we go to gates and then we go to controlled buffer. And here is the documentation of what a controlled buffer is. Okay, so we zoom in a little bit and read, just the first paragraph. The control buffer and inverter, we're not using an inverter this time, we're just using a control buffer, often called a three-state buffer inverter. Each has a 1-bit control input pin on the south side. The value of this pin controls how the component behaves. When the value of this pin is 1, then the component behaves just like a regular component. It passes through. When the value is a 0, then the output is floating. When the value is an error value, then the output is an error value. Okay, so now we have some terms that we do not understand, right? Floating. That's one term that we have never really talked about. So now the question is, what exactly is floating? Floating in an electrical sense means it is not driven. Oh, great. Now we have another term that we do not understand. What is driven? Okay? In the electrical sense. Okay? In the electrical sense, driven simply means you have an electrical potential applied to a conductor. There's a particular tendency to go one way or another. Okay? I'll give you an example. And I need a conductor of some kind. So, looking for some props. Oh, okay, I got it. Kind of like a paper clip, okay? So a paper clip by itself, which is not connected to any source of electrical charge, is floating, okay? It has no tendency to go positive nor negative. It's going like meh. It's going meh, okay? So you can look at floating as that. Is that okay? Indifferent, not concerned, not motivated. All right? Just like the people who are currently missing, absent from the class. Okay, so what happens as soon as I attach the positive end to this wire? Now it's driven. How is it driven? It's driven high. It wants to have a positive charge, or it is connected to a positive charge. If I have another wire to go back to the negative terminal, current will flow because it has that drive to push current from the positive end to the negative end. Is that okay? What if I use the negative end of the battery to connect to the paperclip? It is also driven, but it's driven in the opposite direction. It's now driven low. It has a tendency, it wants the electrical potential to be low at this point. Is that okay? So when you look at the term floating, it simply means it's not connected to either end of a battery. It's really just a conductor doing nothing, not connected to anything. So it can do whatever it wants. Is that okay? Once it's driven, that means there's a particular force applied to it. It has a tendency to do something, to be at a particular value. Is that okay? Okay. So when the value is 0, then the output of a buffer is floating. If the value of the pin is a 1, then it will just be like a repeater. Whatever it sees in the input, it just wants to repeat that as the output. Okay, excuse me. Let me put this back here. All right, so what we're going to do is we'll take a look at, okay, if we don't know what a pin is going to do or what a device is going to do, then what we do is we add a new circuit, and we'll call this one test buffer, just to test what a buffer does. So we go to gates again, locate a controlled buffer, slap it here, and then we got 2 input pins. Here's 1, here's 2, and 1 output pin over here. And then we just wire up this whole thing like so. And then we run an experiment. Okay? So right now the experiment is running already. The input to the buffer is a 0, but the south pin, which is also what we call the enable pin, is also a 0. So the output is an X because it's floating. We don't know what it is. It's not a 0, it's not a 1, it's just floating. Okay, it's not driven in one direction or the other. The moment we enable the buffer, it will mirror. Okay, it will take whatever value it sees in the input and mirror that to its output. So because the input is a 0, now the output is also a 0. Okay. What if we change the input to a 1? The output mirrors to a 1. What if we disable the device at this point? Then the output becomes floating again. Is that okay? How many people drive a stick shift or have tried? Okay. This is a clutch. It's a clutch, okay? You have the engine on one side and the drive shaft on the other side. And then here's your clutch pedal. 0 means you are depressing, you're holding down the clutch pedal, and therefore you're separating the engine mechanically. The rotation of the engine is now disconnected from the rest of the drivetrain. When this is a 1, you have just released your clutch pedal. Okay? So when you fully release the clutch pedal, what happens? The rotation of the engine is now mechanically connected to the rotation of the rest of the drivetrain. Is that okay? So is that helping? Looking at a control buffer as a clutch. So you're going to try driving a manual again? Okay, so now that we understand what a clutch is, or what a control buffer is, let's go back to the original thing that we were trying to do and say, okay, we got this guy here. What are we going to do with this? Okay, so the first thing we're going to do is to flip its direction. So we click it, and then we say, let's make it face the other direction, face west, like that. And we need to leave some room here. And we also we just want the pin to look right, that's all. And we'll put it right here. Because the problem is, okay, we have to make it 8-bit wide. Okay, fine. So it becomes really just a clutch. But the clutch, who's controlling the clutch now? In other words, sometimes we want to connect this directly to the data pin, other times we want to disconnect it. But what is the determining factor? The load pin, right? But the load pin is actually in the wrong polarity. Because when the load pin is a 1, it means we are reading, which means we want to disconnect the input pin from the data port. When the load pin is a 0, it means it's a write operation, and we do want to connect the input pin to the data port. So we want the reverse of what the load pin is doing. So how do we do, what do we do now? What tools do we have in our bag that can say, oh, if it was a 1, it becomes a 0 now. If it was a 0, now it becomes a 1. What do we do to do that? It's a NOT gate, okay, just a negation. Okay, so we go to gates again, but this time we just pick out a regular negation gate, and then we just take the load pin into the negation gate, or the NOT gate, and then we put it here. So now we have flow control, okay? So now the clutch works in the proper manner. When we want to specify a read operation, like what we're doing now, then the clutch is disengaged, which means we are not going to have a bus fight. We are not going to have the input pin to fight with the output of the data port. Okay. On the other hand, if I want to specify a write operation, poke tool. If we want to specify a write operation, then the clutch is now engaged, which means whatever you specify in with the input pin is now presented to the data pin, which is fine because the data pin is now being a reading pin, so the direction is correct. Question? Nope. Okay. So are we okay so far with this design? So with this, we can just play with a RAM module on its own to understand how it gets certain things done. We can experiment with it. We got 3 minutes left, so which is just enough time for me to describe what your lab is going to be for today. The lab is not due until tonight, okay? So you do have a little bit of time to do it, but I would say do it in the lab as soon as possible. So I'll give you a preview. Oh, I have to republish it. Okay. Misclicked a few things. Clicked again, republish, and then this is the preview. Okay. So this is directly, this is getting you to set up for the rest of the homework assignments that we're going to do. And we'll be using TTP for the rest of the semester. TTP stands for Tax Toy Processor. Okay, so it is definitely not a useful processor. It's just a toy for educational purposes. So we start with downloading the Logisim file that we need. You go to this folder, and then you have to download 3 specific files: ALU, processor, wdpc2.circ, and regbank.circ. Okay, so it gives you the instructions of what you need to download and how to open it in Logisim and stuff like that. So if you do not have Logisim with you on a thumb drive, you just have to re-download it at the lab or do it at home or some other place. Okay. After this step, it's really just step-by-step instructions. After finding the missing libraries, Logisim will ask you blah 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 blah. Okay. Examine the ROM component content. What is the content at a particular location? So I just want you to learn how to navigate in ROM and differentiate what is the address as opposed to what is the content of a certain location. Okay? And then the next one says, note that a ROM does not include software programming opcodes, blah, 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 blah. It only contains the microcode. So it's explaining certain concepts at the same time that you have some activities that you need to do. The code that actually can be specified by a programmer is in RAM. And so we have some documents here. And you can open these if you want to. You do not have to open it if you say, OK, I can learn it later. The syntax of the mnemonics is explained in a separate manual, and so on and so forth. Based on these 2 documents, what is the opcode in base 2? No space in the number, use all 8 digits to do a subtraction of register B from register D. So I guess you do really have to go read the documents. Okay, but you have the whole day to do it, so that means you can spend your time to read and understand these 2 documents. And as you can imagine, writing an entire program is troublesome. So the assembler is actually a Google spreadsheet. And you will need to make a copy of this into your own Google Drive in order to change it. And then you want to copy and paste a program into it, and then assemble, and then figure out what is the content at location 8. And then this question asks you to load the program back into the processor, so it will be able to run it. And then question number 7 is telling you, when to stop the execution of the program, so that you can report back a certain result that I want you to report back. Okay. So we are running out of time in the lecture. I can do some demonstration related to the homework assignment at the lab. So I think that's what I'll do. So go to the lab, because it's going to be helpful to understand the concepts behind the homework assignment.